Assalamualaikum warahmatullahi wabarakatuh and hello everyone. In this video, we're going to learn the final subtopic for chapter 4, metallic bonding. To explain about metallic bond, let's use specific metal as an example. So we have magnesium in here. Magnesium is a metal with atomic number 12, means it is located in period 3 group 2. Its valence electronic configurations is 3s2. So this magnesium containing 2 valence electrons in 3s orbital going to remove the 2 electrons to form cation of magnesium ion Mg2+. So we know in the solid states, the metal atoms are packed as close as possible. So all these magnesium atoms in the sample will contribute their valence electrons to form electron C that is delocalized over the entire solid. Delocalizations of electron here means electrons in an atom or ion or molecule is not associated with any single atom or any single covalent bond, means they can move around freely. So the electrostatic forces that formed between this positively charged metal ion and also the sea of delocalized valence electrons results in the metallic bond. So this sea of electrons here will act as a glue that prevents the ion of the like charge to repel with one another. The sturdiness of metallic bond, which can be seen from the way they are formed, somehow convinces us that metals have so much properties to offer. So metals possess high tensile strength, means they can stretch without breaking. So this is due to the valence electrons being very light, thus can move in the electron sea from one position to another in the metal. So if you can recall this from the sea of electron model we have learned just now. So because of this, metals are said to be malleable, means can be drawn into sheet. So as you can see here, we have an example of aluminium sheets or sometimes jewelry. And then they are also ductile, means they can be pulled into thin wires. In regard to those delocalized electrons, means energy can be transferred rapidly. Therefore, metals are also good conductors of heat and electricity. To help you see why metals are said to be malleable and ductile, we're going to take a closer look on how they can be drawn into sheets or pulled into wires. So metal atoms, when they are located next to each other, they're going to form metallic bonds. So we have layers of cations in blue, in sea of electrons here in red. So hammering will cause the layers of cations to slide over one another. However, they didn't break after sliding over one another. This is due to the delocalized electrons that prevent the repulsions between the cations. So the changes in the positions of the metal ions brought about the reshaping the metals accommodated by redistributions of valence electrons that proves that metals are malleable and ductile. In contrast to ionic compounds that has electrostatic forces between different like charges, positive and negative, hammering will cause the ionic bond to break after sliding over one another due to the repulsions between the same charge of ions, positive and positive, negative and negative. They will repel each other because they don't have any delocalized electrons to act as a glue, just like in metallic bonds. Due to strong electrostatic forces of attractions contributed by the metal ions and the free-moving electrons, metals are said to have moderate melting point and high boiling point. So why one is moderate and another one is high? Well, it all depends on the attractions between movable cations and the mobile electrons during particular process. So melting point is obtained from melting process where a given solid will melt. From here, we know the change of states of matter takes place in solid is arranged closely together, which possess only vibrations, to become particles in liquid that are still close together but with no regular arrangements. So this indicates the attractions between movable cations and the mobile electrons need not be broken, hence indicates the moderate melting point. In contrast to boiling process in which liquid boils and turns to vapor, boiling will require more energy in order for the forces to be broken, as particles in gas are well separated with no regular arrangements. Even though liquids also got no regular arrangements, but their arrangements of particles are still close together as compared to gas. The strength of metallic bond is influenced by two factors. The first one is number of valence electrons. So by having more valence electrons means there will be more delocalized electrons. So the attractions between positive ions, which comes from the nuclei, and the delocalized electrons will become stronger, hence results in stronger metallic bond. Another factor is the size of atom. So having smaller size of atom will have greater attractions of positive ions and delocalized electrons. Lastly, metallic bond is strong. These two factors can be concluded if we compare metals located across period 3. So we have sodium, magnesium and aluminium. So by increasing the number of valence electron, here we have 1, 2 and 3 will result in a smaller size of atoms. Hence, stronger metallic bond will be formed from sodium to magnesium to aluminium. Now we're going to look at variations on bonding points at certain period or group. We'll start with period 3. So period 3 elements all have different number of valence electrons. In order to form metallic bonds, the first 3 elements will share their valence electrons to the neighboring metal of the same element. Let's say we have sodium and sodium and sodium, magnesium, also the magnesium and magnesium, just like that. So across period 3, valence electron increase as well as its delocalized valence electrons. So this will result in the stronger attractions between the positive ions and also the delocalized electrons, which then results in stronger metallic bond. So these stronger metallic bonds tells us more energy needed to overcome the forces between them. Hence, bonding point increase from sodium to aluminium. For the second variations on bonding points, we're going to look at down group 1 trend. So group 1 elements share their valence electrons to form metallic bond. Down group 1, the size of an atom gets bigger, which then results in weaker metallic bonds. So these weaker metallic bonds tells us less energy needed to overcome the forces between them. Hence, bonding point decrease from lithium to francium. As for the last variations on bonding points, we're going to look at down group 17 elements. So we know already group 17 is considered as non-metal, so they don't have the ability to form metallic bonds between their atoms. Therefore, they're going to share their valence electrons to form molecules with only weak London forces between them. So down group 17, the size of an atom gets bigger, which then results in stronger London forces. So these strong London forces tells us more energy needed to overcome the forces between molecules involved. Hence, bonding point will increase from fluorine to iodine. That's all you need to know for metallic bonds, and this marks the end of the chapter 4 chemical bonds. Thank you.